the last class, that means on Monday, we actually saw some properties of central force, like the energy is conserved, the angular momentum is conserved, and we also saw that if we actually want to write down the Lagrangian, we can write it down in the form of an equation Fr, okay, which can be written as minus of 1 by r square and so on. So these ideas we already have now, and now we are going to proceed to the next topic, which we call as the Virial theorem. So the probable question, which I actually have asked to your seniors also last time, I think, that's nothing but state and prove Virial theorem. Okay, so this will be an important question, and this will be a descriptive question as well. Okay, 4 to 5 marks is okay for this. So let's read into some of the introducing lines to this particular theorem. Okay, so let's say we have got the conservation law. Okay, we already know about the conservation law for a system of interacting particles which has already achieved a dynamical equilibrium. So you understand this from classical mechanics as well as statistical mechanics, that this achievement of dynamical equilibrium might be time dependent. So let's say if a system is there for a very long period of time, more or less it is achieved a dynamical equilibrium. But this is a very strict rule, okay? If you are considering the temperature, the surroundings that you have, okay, and the weather has changed, it has become winter, and you know that the temperature outside is let's say 5 degrees centigrade, okay, the chances are that the inside the temperature is also 5 degrees centigrade, and that means it has achieved a dynamical equilibrium kind of thing, okay. But then here we are not talking about that larger system. We are considering a normal standard system which is actually in dynamical equilibrium and does not change much with its property, okay. Now this theorem was actually given by Rudolf Clausius, okay, in the year 1870. So you know this is actually related with a bit of science, and this has been there for a very long time, okay. And the interaction that we have here basically, okay, is nothing but considered to be of central force type. So if we have the particles, okay, within the system, these interacting particles there, okay, this scanned, the missed part is there, particles, okay, this is particle. So the particles will actually interact with each other, and this interaction will be central in nature. So that means it will depend on the distance between these two. Okay? That's very important. So let's just do the setup of this. Okay, so I'm going to explain everything step by step. Okay, so it's important, just concentrate here. So what we have here is, let's consider an interacting particle. So all of these particles are actually interacting with each other, and they have also achieved dynamical equilibrium. Okay, so the question is, what do I mean by dynamical equilibrium? In simple word, it means that it's not that the particles are not moving. They are moving, no doubt, and for that they will have a kinetic energy. Okay, and if they have a kinetic energy, they are dynamic in nature. Okay, so in general, we can say it does not have any interaction with the outside atmosphere. Okay, what it has achieved, it's there. Okay, so if I say a kinetic energy of a particular particle is this, I assume that the kinetic energy will remain that. Okay. So if T is the total translational kinetic energy and W be the virial of the system. So see, the term that has been introduced here is called virial, okay? And virial is more or less equivalent to something like a work done, okay? Because you see, if you define virial in mathematical form, you basically have a force and the positions dot product, okay. So that means the unit is Newton meter, right? So if the unit is Newton meter, we are basically considering it to be nothing but a work done expression, okay. So this is basically called a virial, okay. So you know virial variation, okay. So if I'm not wrong, the term virial comes from the term variation, okay. So if we say that the virial of the system is constant. So if I look into the term, F is nothing but the net force of the ith particle. So please remember, we are actually considering the forces acting on all the particles. So I start from I is equal to 1, then 2, then 3, and so on. So if I know the number of particles, I can actually find out what is the net force on the ith particle, and add them up and find out what is the total force acting in the system. Okay, and this is something which is also statistical in nature. Since we already have a good idea about statistical mechanics, this should not be very difficult, right? And then what is Ri? Ri is the position vector of the same particle. So we are considering a single particle here to understand the system. It's very simple. What does Virial theorem state? So the statement of Virial theorem is very important because it says state and proof. So the statement is, the Virial theorem states that under dynamical equilibrium, 2t plus w is equal to 0. What is this t? This t is nothing but the kinetic energy. Okay, so this t is the kinetic energy. So whenever you give a statement, let's say I have asked you what is the statement for or state Virial theorem, right? You just don't write down these two lines. Okay, just start with this. The Virial theorem states that under dynamical equilibrium 2t plus w is equal to 0. Okay, where w is the virial of the system given by this, where Fi is this, Ri is this. Okay, that will be a standard way to write, and T is the kinetic energy, and that's all. Okay, that's the definition that is needed. Okay, you don't need to write down whatever I've written before. Okay, this is just an introductory part. Even if you don't write down, that's fine. Okay, no problem. But statement should be complete in itself. If you're giving a statement, writing down an expression, what does those terms mean is a very important part. Okay. Now let's prove Virial theorem, and you will see that we are not going to use a direct method. We are going to do a lot of indirect things here. Okay, so let's start proving the Virial theorem. Okay? So this is the proof. So let's get it. Okay. So if you write down the equation of motion of the ith particle, see, we are talking about kinetic energy. Then it's only advisable to start with an expression of equation of motion, right? So we have got the equation of motion of the ith particle. So ith particle means we are talking about mass into acceleration is equal to force. So this is the force of the ith particle, this is the mass of the ith particle, and this is d2 ri dt square. Okay, ri is the position vector, so this is nothing but the acceleration of the ith particle. Okay, let's find out the Virial theorem. Our aim is to prove that 2t plus w is equal to 0. Okay, so we are going to find out all the terms one by one. Let's find out the Virial of the system now. So what is the Virial of the system? W is equal to F dot Ri, right? So we can just write down F here. We've just now written what is F, so we can just replace F here and dot Ri. Okay. So this is the Virial of the system. Now we are going to just play around a bit, and we are going to do some kind of modification here. Okay. So you see this term. Okay, this is very important. Don't get confused here. In most of the books I've observed they directly jump from here to here, but how they don't say. Okay, because you get a bit confused here. Why? You see, this is mi d2 ri dt square dot ri. Okay, that means this ddt of dri dt is there. It has nothing to do with this ri, right? But then you see here what is done is mi, this can be written as mi d dt of dri dt dot ri, minus is there. You have no idea why this minus comes from. Okay, we get confused here, and then it is written mi, and then this dri dt is kept separate, and the other ddt is multiplied with dri dt. Now where does this come from? Okay, so this is the idea that I've given. So if you remember in exam, you can write it directly, but I suggest don't do that. You explain why it is there. Okay, so let's take this back. Okay, let's take this expression. So this is what we are taking. Okay, you paid say okay. So we can take this. Okay, so see this now. So what is this? This was the expression m ddt of dri dt dot ri bar. Okay, and how do I get from here to here? How do I get from here to here? So what you can do is we don't have this. Okay, we actually have this in the original expression. Sorry, I think this is something which I should correct here. Okay, so that you are not confused. This is not the one which is there in the original expression, right? In the original expression, if you see, okay, maybe I can take it on the same page and take it there. Original expression, we have this. Okay, let's get back. So this is your original expression. See, this is your original expression. We have this. Okay, so how do I modify this? We can simply write down this in this way. First, let's write down mi d dt of dri dt dot ri. So this is nothing but differentiation of two functions, right? So you can take first function and differentiation of second function plus second function differentiation of the first function. So this is what is done. D dt of dri dt is gives you this dot of this, which is this term, and then mi dri dt dot dri dt. Because d dt will be again for the second term, it will be here. So you do this differentiation and you get the expression. Now it's very simple. You are going to find out this. You need this actually. So you just take this on the other side and you get a minus sign, and this is how you replace it. Okay, so this you take it on the other side and you just replace it. So I think it should not be very confusing. You have to practice it once and it should be very simple. Okay, and then one more step that I need to do is this. So now let's get back into the expression. You see what the expression is, this. Okay, mi d dt of dri dt dot ri. Okay, So what I can do is this. I can write down the expression in this form now. This minus this. Again the question comes how. So again I've done few more calculations here. So let's try to differentiate this part. Let's try to differentiate this part. Okay, half d2 dt square into mi dot ri. So I can take the half outside. This will be ddt of mi ri dot square. Now mi is a constant. I can just avoid it and keep it outside, right? And then you can take ri square, right? So if you take this term and you differentiate it with respect to ddt, see there are two ddt's here, d square dt square. So one ddt I've kept outside and one ddt I've taken inside. So if I take ddt of ri square, it will be nothing but 2 ri into dri dt, normal differentiation, right? So these two and these two will get cancelled. I'll get ddt of mi dri dt dot ri. Okay, so you see this m is there, dri dt is there, and ri is there. Is this the term? Yes, this is the term. Okay, so look into this now. See, this is the term mi ddt of dri dt dot ri. So this is the term that we have, and this term actually can be written in this form. You can do it the reverse also. You can just simply write down this expression, introduce a half here, introduce a 2 here. Okay, now the thing is, how do you remember this in exam? Okay, the point here is that you have to remember it step by step. That's very important to make, and there are certain adjustments that we do mathematically, so those steps has to be remembered. Okay, so when Clausius was doing this, obviously he took a lot of time to understand and do involve the maths here. Okay. Now what about the second term? How does the second term become minus 2t? See here. This is m. This is dri dt, right? And this is dri dt. So dri dt means it's velocity. So this is velocity square. So it is mv square. You divide by 2, multiply by 2, you get 2 times half mv square. So that is nothing but a kinetic energy. So this also I have shown it here, but I think you can understand it. Mi dri, which is nothing but mv square, 2 times half of mv square, which is equal to 2t. Okay, so this is expected that you understand this. Okay, many books I have seen that they don't derive it, and I don't understand why. It should be derived. Okay, otherwise we don't understand things clearly. Okay. Next, let's go to the next step now. Half d square dt square of I. So I think this is not very complicated. See, this is m r square, and if we consider that r is the position vector with respect to origin, okay, then we can simply say that this r is nothing but the radius of gyration, right? If you remember, and then you know mass into r square, radius of gyration square will always give you the moment of inertia. So if you're finding out the moment of inertia, you can just simply write it down as d square dt square into I minus 2t. Okay. So this is what we have observed till now. Okay, so don't get confused here. Let me just give you one quick recap. We start from the virial theorem. Okay, sorry, from the virial of the expression, and virial is fi dot ri. We put it there, and then we do our calculation. Okay, so once we put this, if you practice it once or twice, it should be all mechanical. You should be able to arrive at the final result. Okay, so this is nothing but the virial of the system. So the final virial that we get after doing all the modifications and involving moment of inertia and kinetic energy is this. So whenever you write down in your exam, I would prefer that you write it down very clearly and write down what is I, moment of inertia of the whole system, about the origin and so on. Okay, and this is the total translational kinetic energy. So you see, we got rid of this summation sign also, for the simple reason that we are considering the total now. Okay, we are considering the total of the component that it has. So now, if the system has achieved a dynamical equilibrium, so this is an assumption that we have to do, and it actually does happen. This moment of inertia should not change in time with time. So now you know that what property of dynamical equilibrium is used, not the temperature. Okay, it means that the moment of inertia does not change with time. Okay, so if a system is under dynamical equilibrium, the moment of inertia will be a constant. Okay, so if we consider the motion of the molecule under dynamical equilibrium, it will keep moving, no doubt, but then the molecule is not going to change their position much. If it does not change their position much, the center of mass is not going to get shifted. If the center of mass doesn't get shifted, That means the moment of inertia will more or less remain same. Okay, so I should not change with time. So that means I can simply write it down as di dt is equal to 0. If di dt is equal to 0, d square I dt square is also equal to 0, right? So what does it mean? That means this part will actually become 0, right? So if this part becomes 0, we have got w plus 2t is equal to 0. And that is why understanding what is dynamical equilibrium is important. Then only you can get w plus 2t is equal to 0, right? So I understand this. This is 0, this is minus 2t, it goes on the other side, you do the expression, you get that. Okay. So this is what is Virial theorem is all about. Okay. So when you write down in your exam, I would expect that you also show the intermediate steps. If you skip, still I might give you some mark, but then it's preferable you explain everything in detail. That's important. Okay, so there are some special cases, and of course we might be thinking that what is the application of this Virial theorem? Well, we are not going to go into a very detailed application of the Virial theorem, but then we are definitely trying to understand what is the application part. Okay, we're not going to the mathematical part. We will try to understand this. So the theorem is basically used in case of kinetic theory of gases. So you understand that this theorem will also have application in statistical mechanics. Okay, so if you're considering a gas, it might be a classical ideal gas, and we can use the Virial theorem there. Okay, and then you can actually use to prove the Boyle's law. Okay, so for perfect gases, so you know perfect gas PV is equal to nRT. Okay, so every type of these expressions can actually be understood better if we use Virial theorem. Okay, and then of course we can also obtain the equation of state of imperfect gas. So you understand that there is perfect gas, there is imperfect gas also. Okay, so these can be done. There is one more part that we actually like to just look into, that we have the Virial theorem is w plus 2t is equal to 0. Can this Virial theorem can also be written in terms of potential? Okay, now let's see how we can do it. Okay, so we are going to write this Virial theorem in terms of potential. Okay, so this is the application part. Okay, don't get confused with the next part. This is not the proof of this. Okay, this is just an expression. This is a different topic altogether. Okay, so can we write down the Virial theorem in terms of potential? So we have T is equal to minus half P, if you just minus half W, sorry, if you just look into this. Okay, or this T, which is nothing but the kinetic energy, is minus half, and the Virial is F dot R. Now if you go back to your previous class knowledge, okay, younger class knowledge, what you see is that the force is nothing but the positional derivative of the potential. Okay, so we also saw this in classical mechanics in the earlier chapters also. Okay, and we do this in terms of the generalized coordinate, and we call this as the generalized force and so on, right? But I think this is also something which you have done in the lower levels. Okay, not only now. So we have this minus half of summation I, and let's say this is a molecule, and in a gas system it might not have just one axis, it will have let's say 3 axes. Okay, so if we consider that, we basically have to take just the gradient. Okay, so the gradient and del are more or less are relevant. Okay, one is in 1 dimension, one is in 3 dimension, and so on, dot r. Okay, so if we just consider the summation, okay, and if we just consider it in, this is the general statement. Okay, and if we just consider this to be minus of del v del r, we can just replace it. Okay, and this is del v del r to r. Okay, so if we are considering this, okay, so this you might have done it before. Okay, this is actually applicable in case of an ideal gas. Okay, and depending on this value of n, we can actually say what is the form of potential. Okay, because you know we do say that sometimes the potential is minus of k by r square. Okay, where does that r come from? That r comes from what is the value of n. Okay, so when it is by r square, this n would be nothing but a minus of 3, right? So if this is minus of 3, we're basically getting minus 3 plus 1, it will be minus of k divided by, sorry, k divided by r square. So that will be the potential form. So this is the general form of the potential that we have. Okay, so I cannot really say whether you've derived this or not, but then for now, in order to understand this, just remember this. Okay, this is a general form of the potential energy. So can we take del v del r? Yes. So if we take del v del r, this will be nx to the power n minus 1. So n plus 1, k is a constant, r to the power n. And we can actually replace it there. Okay, so you can just simply replace it. So t is equal to half of n into kr to the power n into r. Okay, so this is half of n k r to the power n plus 1. Okay, so you do have an additional r here, so it is r to the power n plus 1. So this can be written as half n plus 1 into v, because what was kr to the power n plus 1? This was nothing but v. So you see v is kr into the plus n plus 1. Okay, so we have this, and then if we consider the inverse square law in this particular case, the value of n would be nothing but minus 2. Okay, that minus 2 is a different case altogether, but if we consider the inverse square law, n would be minus 2, so we can just replace the value of n here, and then we can get t is equal to minus half v. Okay, so this is minus half v. So if you just do your maths, okay, do the algebra, you have 2t plus v is equal to 0. So this is a special case of Virial theorem where we are including the potential energy. Okay, we are including the potential energy. So this is actually, please consider this as a special case because this might not be applicable everywhere. Okay, the Virial theorem is this, but then in some cases, if we have the form of the potential energy as kr to the power n plus 1, okay, and then we can actually write down this also as w plus, sorry, v plus 2t is equal to 0. Okay, so what do I understand from here? I do understand that the kinetic energy and the potential energy will actually be 0. So that means if we consider this in this way, why does this 2 comes into the picture? That's a different case, but in general the kinetic energy, potential energy will actually be 0, okay, for the entire system. Okay, but then that is a special case. So this is what is Virial theorem is all about. Okay, this is what is Virial theorem is all about. So for your exam, I might ask you a derivation, and if I go for the special case, I might ask you that show that the Virial theorem in terms of potential energy is 2t plus v is equal to 0. Okay.